Okay, so let's begin. So as we discussed yesterday, uh, I gave a few slides on SKLearn with the example of the blood transfusion data. Now on Thursday, you will be specified a particular data set and classification task. You know that support vector machines are binary classifiers. Okay, so the task will be specified to you, and you will have to find out precision, recall, F-score, etc., which we had yesterday discussed with the example of something like a Venn diagram. Okay, the concept class and the label class from the classifier. Then we started hidden Markov model, and in hidden Markov model, the main task is to do sequence labeling. We took two examples, one from computer vision, where this sequence of postures is showing how a person is going through a sequence of postures, finally lifting a box and standing. So in between we have the postures which are half bend, bend, down squat, sit, up squat, half stand, and stand. We saw that two postures may look alike, just like two words may look alike, but with different meanings. Now, down squat and up squat look very much alike, but if we know that the previous posture was sit, then the next posture has to be up squat, cannot be down squat. So you see what happens here is a notion of transition, right? And every state, we'll call them the state, down squat, sit, up squat, etc. states. State to state, there are transitions. And from sit, the probability of transition to down squat is zero, almost zero. Okay. But the probability of up squat is very high. And the probability of going directly from sit to half stand, holding the box, is possible, but probably with less probability. Okay, so we are getting a sense of transition from one state to another. Okay, and at every state, the observation is the person's posture. The postures are the observations, and the labels for the states are to be given. So labels are called the hidden states or the hidden variables. Okay, so the postures are states and the labels are postures are observations and the labels are the hidden states. So this is a situation which requires sequence labeling in computer vision scenario. So we took an example from language also, where we took this sentence to bank, I bank on the river bank. So the same word bank appears multiple times, but with different roles and meanings. Here also we have a sequence labeling problem. We have to give part of speech label to each of the words. So to, for example, is a preposition. The next bank is a verb. But the bank at the end is a noun. Okay, so it requires disambiguation. For example, bank is both a verb and noun. So previous word and other clues will disambiguate. So here also in the word sequence, there is a notion of transition probability and observation probability. So the observations are the words at every position. Okay, and states are the labels, the part of speech labels which are hidden. Okay, they have to be found out. So these problems are typical in AI. In real life, we encounter such sequence labeling problem all the time. Okay, and the machine which is used for such purposes is hidden Markov model. And hidden Markov model are based on what is called the noisy channel model. The noisy channel model says that in comes a sequence, out goes another sequence, and input to output mapping is typically one to many. And there is also a possibility of noise in the channel, imperfection in the channel. So for example, if I am hearing a speech and transcribing, then I as a channel have my imperfections. Okay, these imperfections cause me maybe not understand the word perfectly and transcribe it. So that's why we have to necessarily invoke probability, and the T star, which is the best possible output sequence, is obtained by what is called the argmax computation. The argmax is a search process. It searches for the best possible T given W, where best means highest probability. So choose that T which has the highest probability of T given W. It's a conditional probability. So if we work with conditional probability of T given W, we say we are operating with what is called the discriminative model. But if we apply Bayes theorem, okay, and then take these two components, the prior probability Pt and probability of W given T, the denominator can be ignored. Then Pt into Pw given T is actually joint probability of T comma W. So this joint probability being used takes us to what is called the generative model. Okay, so discriminative model and generative model. Typically, generative model is more time consuming and data hungry because it is a joint probability situation. But it can work without lots of other properties of T and W, the features, okay, which we will see at some point of time. What do we mean by features? Okay, now let's go to the machine as such, which is the hidden Markov model. This was being illustrated with the example of three containers, U1, U2, and U3. We are choosing a ball from the container with replacement, and we go from one container to another or remain in the same container with the following transition probability table. I remain in U1 with probability U 0.1, go to U2 0.4, go to U3 0.5. And the probability of picking up a particular colored ball is as per the number of balls inside the container. So probability of picking up red ball given U1 is 0.3, green ball 0.5, blue ball 0.2. So this is expressed quite neatly by a probabilistic finite state automaton. Okay, so finite state machines you have done in your theory of computation course or discrete structures. So the additional thing here is the probability. The probability, the transition from U1 to U1 is shown here by this arc, and the probability value is marked on this, which is 0.1. U1 to U2 is 0.4, and so on. So the transition probability table is expressed, okay, by means of this diagram. We also incorporate the observation or emission probabilities, which are a probability of red ball given U1 is 0.3, probability of green ball 0.5, probability of blue ball 0.2. The observation probabilities have to sum to 1. The transition probabilities also have to sum to 1. Now, the key question, the first question asked is, if the observations are given, I have the ball colors in this sequence, R, R, G, G, B, R, G, R. What is the best possible sequence of containers, okay, which would have given rise to this observation? Best possible means given this observation, find out the container sequence which has the highest probability. Okay, that is the problem being solved. Okay, so there are three classic problems with respect to hidden Markov model. Given the observation sequence, find the possible state sequence, best possible state sequence. This is done by an algorithm called Viterbi. Given the observation sequence, find its probability. This is done by an algorithm called forward-backward algorithm. And given the observation sequence, find out the HMM parameters, that is the transition and observation probability values. This is done by what is called Baum-Welch algorithm. Okay, so now let's define hidden Markov model formally. The hidden Markov model is defined by n, the number of states. It is a finite state machine. M, the distinct observation symbols for the urn problem. There are three observation symbols, R, B, and G. The number of states is 3 there, U1, U2, U3. State transition probability distribution A, Aij. Aij is what is the probability of transiting to state J being in state I. The observation symbol probability distribution in the state J, B. So B is BJK, the probability of emitting symbol number K in state number J. The probability of observing red ball given 1, which means container 1. The initial state distribution pi, which is pi I. So which urn will you start from? U1 or U2 or U3? Okay, so that probability distribution is also given. And that probability, of course, the values have to sum to 1. So I hope the formal definition of the hidden Markov model is clear to you. States, observation symbols, transition probability, observation probability, and initial state distribution probability. So the notation wise, Aij is probability of Qt plus 1 equal to Sj given Qt equal to Si. Okay. I and J vary from 1 to n. So what is the probability of taking up state number J from state number I? Bjk is defined as probability of Vk at t given Qt equal to Sj. J goes from 1 to n, K goes from 1 to m. So probability of observing observing symbol K given the state Sj, okay, given state number J. And pi I, probability of Q1 equal to Si, going from 1 to n. So state transition, observation probability, and initial probability distribution. Now we come to observations and states. We were given RR, GG, BR, GR. So the states are O1, O2, O3, O4, O5, etc. I mean, these are the observations. O1 is R, O2 is R, O3 is J, and so on. States are S1, S2, S3 up to S8. So in our case, the container problem, U1, U2, U3 are the states. S is the state sequence, O is the observation sequence. S star is the best possible state or urn sequence. So we have to maximize PS given O by choosing the best possible S. So this is the problem. Maximize probability of S given O, where S is the state sequence and O is the observation sequence. We obviously have to perform this computation. S star equal to argmax S, probability of S given O. Now, probability of S given O, how do we obtain it is the question. Okay. So here we'll have to apply Bayes theorem. Okay, there is no other way of solving this problem. You cannot directly compute probability of S given O. So argmax over all possible S, probability of S given O, is prior probability of S into probability of O given S. Now comes the mathematical manipulation. Probability of S is probability of S 1 to 8, the sequence of states from 1 to 8, which by chain rule is probability of S1 into probability of S2 given S1 into probability of S3 given S1 and S2. This is the notation S1 to. Probability of S4 given S1 to 3 and probability of S8 given S1 to 7. Now we make what is called the Markov assumption, k equal to 1. Probability of S is equal to probability of S1, the first state. Probability of S2 given S1, probability of S3 given S2, S4 given S3, S8 given S7. Now all these probabilities are these known. Yes. What is the probability that S1 corresponds to the first urn or second or third urn? This comes from the initial probability distribution. Probability of S2 given S1, let's say U2 given U1, this is known from the transition probability table. So all these state transition probabilities are known from the transition probability table. What about probability of O given S? Again, apply chain rule and see that this probability of O1 given S1 to 8, probability of A2 given O1 and S1 to 8, probability of O3 given O1 and O2 and S1 to 8 and so on. We are applying chain rule of probability. So now we assume that the observation depends only on the state and nothing else, not previous observation and not any other state than the state currently being considered. So probability of O given S will be probability of O1 given S1, probability of A2, O2 given S2, up to probability of O8 given S8. We are considering the observation RR, GG, etc., where there are 8 observations. So what we come to is probability of S given O is probability of S into probability of O given S. This equal to is to be taken with a pinch of salt. It is equal to with the assumption that with the understanding that the denominator probability of O is dropped. Okay, it is because of the argmax computation, which is probability of S1 into probability of S2 given S1, S3 given S2 and so on, and into probability of O1 given S1, O2 given S2 and so on. So we have obtained the transition probabilities of states and the observation probabilities. So from this, we can begin to group terms. Okay, probability of O0 given S0 into probability of S1 given S0. This is a grouping. And probability of O1 given S1 into probability of S2 given S1, O2 given S2, S3 given S2, and so on. Okay, so this kind of grouping is done. So after we group them, we have another equivalent automaton. This automaton is this. This arc is now given a different meaning. This arc is probability of U1 given U1. The next state is also U1, and multiplied by probability of R given U1. Okay, so why are we able to multiply the probabilities? Because of these steps. We take components of transition probabilities and observation probabilities and multiply them. Okay, so the automaton which was here U1 to U1, U1 to U2, U1 to U3, etc. And these transition probabilities were obtained. And we had observation probabilities also. Okay, R, G, and B coming from a state. What we do is that we simply multiply probability of R given U1 and probability of U1 given U1. So this becomes 0.03. Here it is. So R comma 0.03. What is this probability? 0.03. The probability of picking up a red ball from U1 and also remaining in U1 in the next state. So this is the product. Okay. And this product we can take because of this algebra, because of this grouping of terms. Okay, so then an automaton which was explicitly showing transitions and observations is converted to another automaton, which is the joint probability of state transition and observation. Okay. So now we have this new automaton, and we have a very useful notation here now. Probability of OK given SK into probability of SK plus 1 given SK is given a notation which is very intuitive. This is probability of SK arrow SK plus 1 with OK on top of the arrow. This is transiting from state SK to SK plus 1, observing OK, the symbol OK, whose meaning is this joint probability. Probability of OK given SK into probability of SK plus 1 given SK. Okay, so now we can look upon this whole situation as what is called a Markov chain. Okay, state to state transitions, and on each arrow depicting transition, there is a symbol. So we have a Markov chain to capture the situation. So any question? So the key points here are, first of all, making use of the transition and observation probabilities to create a finite state automaton, showing observations and transitions explicitly. Then merging the observation and transition probabilities. Merging means we take the product of them, and having another automaton which has observation and state transition merged together. For a sequence leveling situation, this kind of product gives rise to what is the Markov chain. And a very useful notation is probability of SK going to SK plus 1, observing or emitting OK, which is actually nothing but the product of two probabilities, probability of OK given SK and probability of SK plus 1 given SK. Okay, so this is where we have reached now. So now let us see, with this probabilistic FSM and with the observations and transition, what can we do? So here is a simple probabilistic finite state machine, also a hidden Markov model, where the Markov window is 1. Okay, a state depends only on the previous state, and the future state depends only on the current state, nothing else. Observations depend only on the states, nothing else. So we have two states, S1 and S2, and there are two symbols, A1 and A2. So we can remain in state S1 with observation A1 with the probability 0.1. We can remain in S1 observing A2 with probability 0.2. Okay, and then from S1 to S2 with A1 0.3, S1 to S2 with A2 0.4, S2 to S1 A1 0.2, S2 to S1 A2 0.3. and S2 to S2 with A1 0.3, S2 to S2 with A2 0.2. So these probability values are actually transition probability and observation probability merged together. So what is the most likely state sequence given an output sequence? So let's see how to compute this. So suppose the output sequence is A1, A2, A1, A2. Okay, A1, A2, A1, A2 is the output sequence. Now we have to find out what is the most likely state sequence. Okay, given this information on the automaton. So let's start. At the start, we observe nothing, emit nothing. So let's say the initial probability distribution is such that you always start with S2, S1. So start to S1 emitting epsilon, the probability is 1. Start to S2, the probability is 0. Okay, and then therefore this part of the tree will not be considered in future because initially itself the probability is 0. What happens in S1? In S1, I observe A1 and I go from S1 to state S1 with observation A1 with 0.1. That was given in the FSM itself. S1 to S1 with A1 0.1. I go from S1 to S2 with observation A1 with probability 0.3. S1 to S2 0.3. Then the observation is A2. So S1 to S1 with observation A2, the probability is 0.2. S1 to S2 0.4, S2 to S1 0.3, S2 to S2 0.2 as per the FSM given. Now something important happens. So that is the heart of the Viterbi algorithm. Okay. What happens is that we have to take the whole path starting from start to S1, S1 and S1 here. So on the way, whatever probability values are there, we keep multiplying them. So here the accumulated probability is 1 into 0.1, which is 0.1. And after this state, the accumulated probability is 0.1 into 0.2, which is 0.02. Here, the accumulated probability is 0.04. Here it is 0.09, 0.06. Now what happens is that we consider all the paths which end in the same state. Okay, so you have to mark this point here. This is the heart of the Viterbi algorithm. So how many paths are ending in state S1? 2 paths. Start S1, S1, S1. Start S1, S2, S1. Out of these 2 paths, the path with the lower probability will be shut down. The path with the higher probability will be retained and further advanced based on the next observation. So you can see here, out of these 2 paths ending in S1, this path has the probability 0.01, the other path is 0.02. So this path S1, S2, S1 will be retained. The path S1, S1, S1 will be killed off. There are also 2 paths ending in S2. And we find that the path ending in S2 here is 0.04 probability. The other path ending in S2 has 0.06 probability. So we will retain this path here and kill off the other path. Okay, so now we'll have to only consider these 2 paths and their advancement. All right, so we had accumulated probability of 0.09 for a path ending in S1 and 0.06 for the path ending in S2. Now the observation is A1. So S1 to S1 on A1 is A1, S1 to S2 on A1 is 0.3. So the accumulated probability here is 0.09 into 0.1, which is 0.009. And here 0.09 into 0.3, which is 0.027. Here, the accumulated probability is 0.06 into 0.2, 0.012. And here 0.018. Now, there are again two paths ending in S1 and two paths ending in S2. Out of the two paths ending in S1, I will retain this path here. You can see the tick mark. And out of the two paths ending in S2, I'll retain this path, 0.027 and 0.018. The last observation is A2. So only these two nodes will be advanced. Other two paths are killed. So S2 to S1 with observation A2 has probability 0.3, giving rise to accumulated probability of 0.0081. S2 to S2 with observation A2 0.0054. S1 to S1 0.0024, S1 to S2 0.0048. So this finishes the whole observation sequence. And we have been able to find out the best possible path, which has the probability of 0.0081. This is the path which will be taken. Now, if we do back tracing, then the path is ending in S1 through S2 through S1. Through S1. So then again through S2, S1 and start. So the path is start S1, S2, S1, S2, and then S1. OK, so this is the path. This is the highest probability. Now, I hope you have observed something interesting. What is the complexity of this algorithm? This algorithm, by the way, is called Viterbi algorithm. Okay, one of the most famous algorithms in AI, to be counted as a pillar, just like A-star algorithm, perceptron algorithm, backpropagation algorithm, and so on. So hidden Markov model and Viterbi combination is another pillar of AI. All right. So what is the complexity of this algorithm? This algorithm could have become exponential. Okay, it could have become exponential because at every state you have number of children as the number of states possible. Okay, so after one observation, you have number of states. After the second observation, you have number of states square. The number of states cube, number of states to the power 4, and so on. So if there are n observations, then the tree could have become exponential in size. Okay, it would have been a number of states to the power n, where n is the length of the observation. But that doesn't happen. What happens is that after every observation, we retain only t states. In the next observation also, only t states are retained. Next observation, again, t states are written. OK, you always kill off those paths whose probability values are less. So the complexity of the algorithm, therefore, is t into n. T square into n. Okay, because you have to find out the best possible state by searching amongst the states. So it is an order n algorithm where n is the sequence length, which could have been an exponential algorithm drastically brought down to linear algorithm. And that is happening because of this Markov assumption. And that is the trick in Viterbi algorithm. OK, any question? A very important idea has been described today. Any question? Okay. So do take a look at this particular example, and what is instructive is how the highest probability paths are retained. Okay. You possibly also see that uh, in this whole sequence of paths, you will have to find out those paths which have the higher probability. Okay, so higher probability means you have to carry out a max operation. Okay, so you'll have to find out the max value at after every observation. So that gives rise to the t-square part of the complexity. Okay, so now let's apply this to this idea to sequence labeling. So, for example, we are labeling the sentence here to bank, I bank on the river bank. Okay, we are doing part of speech tagging. So here, the problem is formulated as follows. The best possible tag sequence T star is obtained by argmaxing on probability of T given W. Okay, so probability is introduced because of the ambiguity and noisy channel model. So this argmax over T, probability of T into probability of W given T, Bayes theorem, probability of W, this would be probability of W, and then argmax over T, probability of T into probability of W given T. So remember that this is a part of speech tagging situation. Probability of T is the transition probability. What is the probability of seeing a noun after a verb? Or what is the probability of seeing a down squat after an up squat? What is the probability of seeing a standing position after seeing a sitting position? Okay, so these are the transition probabilities. So if we stick to the part of speech tagging situation, what is the probability of seeing a noun after a verb? What is the probability of seeing a noun after an adjective, and so on? This is the probability. And probability of W given T is what is the probability that bank is a no, what is the probability that given a verb, the word is bank? Not the other way. What is the probability that the bank, given the word bank, it is a verb? Okay, it is because of the way the likelihood is obtained. What is the probability of the word being a bank given verb? Okay, and so on. Now, because of the Markov assumption, the probability of the state sequence can be taken as the product of state transitions. Okay, so probability of T0 into probability of T1 given T0, probability of T2 given T1, and so on. These are probabilities of seeing a particular part of speech given the previous part of speech was something. And then the probability of W given T is again probability of these words given the part of speech. So after all this is done, we can take the product of transitions and observations and then solve the problem just like in the Viterbi algorithm. Okay. Now the question that will arise is that how do you get the probability of down squat given the previous state was bend? Or probability of half stand given the previous state was sit? How do you get these values? Any idea how do you get those probabilities? One or zero? Maybe somebody will go. Okay. So, okay. No, the question is how do you get these probabilities? So you're saying probability will be 0 or 1? No, probabilities are always obtained uh, by the likelihood principle given data. So what we will have is that we will have lots of such data items where the postures and their labels are given. Okay, then you find out in how many sequences there was down squat after bend. Okay, so you find out how many times this happened and find out how many times bend happened. So the number of times down squat happened after bend divided by the number of times bend happened, that ratio will give that probability. So this is according to the maximum likelihood principle. How many times is a verb observed after a noun? So again, you will need data. You will need these kind of sentences and their part of speech tag levels. Okay. In fact, one of your lab assignments will be on this kind of sequence leveling task. You will have to implement Viterbi algorithm and the data will be given and you will have to the sequence, a new sequence you will have to label. So how many times do you see a verb after a noun? So given these kind of data, which are labeled already, find out how many times you had a verb after the noun and how many times you had noun, the ratio of that count. Okay, verb after noun divided by noun, that will give you the probability. So here, the training task is very simple. The training task is simply noting down counts and taking ratio of counts. So the training is very, very simple. It need not be the case for several, very practical problems. For example, in automatic speech recognition, you will require a complicated training algorithm. In discriminative models also you require complicated training algorithm typically. Now let's very quickly introduce another algorithm, the forward-backward algorithm. The Viterbi algorithm you must implement in the lab. Okay, that gives a very nice grip on the algorithm. So there is a code here of Viterbi algorithm where dynamic programming essentially is used. Now let's come to the probability of the observation sequence. So probability of the observation sequence has suddenly become important in the context of language models and large language models. So let me motivate by this example here. Let's take the first sentence, the sun rises in the east. The second sentence, the sun rises in the east. The third sentence, the SVN rises in the east. And the last sentence is the sun rises in the west. The first sentence is perfect, grammatically correct, semantically correct. The second sentence, semantically correct, but grammatically wrong. The third sentence, semantically may be correct, syntactically also correct, but there is a spelling mistake, SVN. The last sentence is semantically incorrect. The sun rises in the west. So something wonderful that comes from the power of data is the following. You can say that this sentence, the sun rises in the east, something wrong with this sentence without knowing English grammar. How? Because the probability of this sentence will be low compared to the probability of the first sentence. Now the question is, what is the meaning of probability of a sentence? The probability of a sentence is computed by sequence probability. What is the probability of the? What is the probability of sun given the? What is the probability of rise given the and sun? What is the probability of in given the sun rise? probability of the given the sun rise in and so on. Apply chain rule and use this. Now, the ball has shifted to another code. What is the meaning of saying probability of the? The probability is actually the question. Given the first position in the sentence, what is the probability of observing the there? Many other words could have come in that position. A could have come, lion could have come. Okay, IIT Bombay could have come. Many other words could have come. So the probability of the is called probability of the unigram. So that probability is found by taking a large corpus. It's called a monolingual corpus, huge amount of data, and find out how many times the appears divided by the total number of words in the corpus. Okay, so that will give you the probability of the word the, and that will be a very high probability because the is very frequently occurring. The probability of the word procrastination will be low because this word is a rare word. Okay, so indeed, the AI community has done this. They have collected huge amount of language data, huge amount of speech data, huge amount of image data. Okay, and use probability to remarkable advantage and observations. Now, these particular sentence will have low probability because this probability of rise given sun and that is called a trigram probability. The rise will have low probability. Okay, if the corpus is a good grammatically well constructed corpus, the sunrise will have very little probability. You will not see this sequence. And because that sequence probability is low, the overall probability will be low. And therefore, you will come back and say that the sun rises in the east is more probable than the other sentence. I think that this sentence has some kind of problem. I don't know what problem it is. It has some problem. When I come to the last sentence, the sun rises in the west will have very low probability because normally sun doesn't rise in the west. The sun doesn't rise in the west. Okay, except in some kind of maybe fairy tale or some kind of mythological discourse. Okay, where some god made the sun rise in the west. So since this is not occurring in the corpus, it has low probability, and then we say that something wrong here. What is wrong? Semantics is wrong. The meaning is wrong. Okay, so the probability of observation has huge amount of importance. A language model is one such situation. Language model means the probability of sentences. So we'll do all that and then see how to compute the probability of an observation sequence. We'll have to introduce the state through marginalization, and we have to use what is called the forward-backward probability. Okay, we'll do that.